So, welcome. Welcome to Café Scientifique. It's great to see such a good crowd tonight. Yeah. Turn up the mic. Is that better? I'll just get a little closer here. Okay. Before we start, I'd like to acknowledge the Lekwungen-speaking peoples on whose traditional territory the University of Victoria is, and this is a University of Victoria event, and the Songhees, Esquimalt, and Wasanic people whose historical relationship continues with the land to this day. We have a real treat tonight with Dr. Laura Ferrarese. Black holes, supermassive black holes, galaxy morphology, calibrating intergalactic distances. This is what made Dr. Ferrarese really... Okay. Supermassive black holes. I feel like a fraud up here. And supermassive black holes, galactic nuclei, galaxy morphology and dynamics, and calibrating extragalactical distances. This is what made Dr. Ferrarese really well known as a scientist. She's a principal research officer of the Herberg Astronomy and Astrophysics Research Center, which is centered here in Victoria. And her work has been very widely recognized and by many accolades. And she's a fellow of the Royal Society and of Canada and many other things. I also understand from a good authority that she is a great musician and loves to play the cello. So without further ado, please welcome Dr. Laura Ferrarese on Exploring the Night Skies.
Thank you. Let me see. I am going to set my timer here, just so I don't go too long with this. Okay. I can shout. I'm Italian, so that's one thing I do really, really well. When Mark and I were discussing what I was going to discuss today, better? Yeah? Okay. Okay, this is going to be the hardest part of the talk will be for me not to move. I don't know if I can manage, but anyway, so when Mark and I were discussing what I was going to talk about today, we thought it would be fun to split the time between talking about my research in the first part and then talk about satellite constellations and their effects on the night sky in the second part. And then after the fact, when I started thinking what I was actually going to say, I realized I vastly overestimated my ability to say anything intelligent in that amount of time. And so what I will do is I will spend a little bit of time, maybe 5 minutes or less, to talk about my research. And then I will move to the other topic, which is satellite constellations, which quite frankly is more interesting. However, because I don't want to have brought you here under false pretenses, I'm quite happy to stick around after the talk and talk to you about my research if you're interested. So I will start with that. As Mark mentioned, I have worked on many different topics throughout my career. But one constant has been the study of and the characterization of supermassive black holes. So why do we call these supermassive black holes? These are objects that reside at the very centers of galaxies. We call them supermassive to distinguish them from the stellar mass black holes that are the results of the evolution of massive stars. And we also call them supermassive because they are supermassive. So these are objects that have masses that are of the order of many tens of thousands to billion times the mass of the sun. So when I started my PhD, which was in the mid-90s, we really had compelling evidence of the existence of a supermassive black hole in only one case, at the center of our own galaxy. And in fact, Andrea Ghez at UCLA and Rainer Genzel at the Max Planck Institute in Germany received the Nobel Prize in Physics a few years ago for proving conclusively that indeed there is a supermassive black hole at the center of our galaxy. But that really, in the mid-90s, was the only case. So when I started my research, myself and other groups that worked on similar topics, we proved that in fact black holes are ubiquitous, that pretty much every galaxy we looked at has a supermassive black hole at the center. It's not just our own Milky Way. So you think of a galaxy as being composed of stars, of gas, of planets, of whatever. Well, supermassive black holes are as fundamental a constituent of galaxies as the stars and the gas and everything else. So this was by itself really quite exciting, but we really were not prepared to the very big surprise that came a little bit later, and this was really something that was completely unexpected. What we did realize as we collected more data is that supermassive black holes are not just a fundamental constituent, so we find them at the center of pretty much every galaxy, but they're actually capable of controlling the evolution of the galaxy as a whole. Now, this really was very surprising to us because supermassive black holes have I call them supermassive, but compared to the mass of the entire galaxy, they're really not very much at all. So a supermassive black hole might have a mass which is a fraction of the percent of the entire mass of the galaxy. So how can these objects at the very center know about what is going on in the rest of the galaxy? The way this happens, we now believe, is as material accretes onto a supermassive black hole, it does release a tremendous amount of energy, some of which is in the form of very powerful winds. Now, galaxies form stars, through by using gas, right? And if you have very powerful winds that expel gas from the center of a galaxy and potentially from the galaxy as a whole, you no longer have the material that you need to form stars. So accretion onto a central supermassive black hole has the potential of depriving the galaxy as a whole of the material that it needs to grow further. So a supermassive black hole controls the formation and the growth of the entire galaxy around it. So this was really sort of caused quite a stir in the community, and this particular observation allowed us to resolve a number of question marks that were open at the time. For instance, at the time we didn't really understand why some galaxies have stopped forming stars a very long time ago, and we now think that this is the reason. So what I'm doing today, and this is actually a project which is led by an ex-postdoc of ours, which is now at the University of Calgary as a faculty member. We are looking at weird galaxies. So galaxies that are somewhat misfits, if you wish. They have properties that are very, very extreme. They don't conform to the classical image of a galaxy that we might have. So for instance, they're very small, they're very compact, they're just a little bit weird. And we are trying to understand why these galaxies are different. And we're trying to understand this by looking at the supermassive black holes at the center. And this is research we're carrying out with the James Webb Space Telescope. And the results are not yet published, so the analysis is actually still ongoing, but the very first indications from this study is that these galaxies have black holes, which are very massive at the center. I mentioned earlier that the black holes we know about have masses that are a fraction of a percent of the mass of the entire galaxies, but in these particular galaxies, the black holes can be 10%, maybe even more of the mass of the entire galaxy. So why is that? our interpretation is that these galaxies used to be a lot bigger, so a lot more massive, and had a ratio of black hole to galaxy mass, which is quite normal. But then through evolution within the cluster of galaxies in which they're found, that they actually lost a lot of their mass, and they're now much more compact, much denser. So this is another way in which the black holes allow us to understand how galaxies evolve. So I think that was probably more than 5 minutes, and I realized it was probably very confused. However, as I said, if you have questions about this, I'm quite happy to stick around after, after the fact, and talk to you for any length of time you wish. So now I would like to sort of turn the page and move to the second topic, which is satellite constellations and their impact on the night sky. So my own personal first encounter with a satellite was back when I was a PhD student. So the research that I just mentioned was conducted using data from the Hubble Space Telescope. And so I was looking at the images I was using for my PhD project, and I noticed that one of them had a streak running across the frame. And I really didn't know what that was, so I went up to the office of my advisor, and I showed him the image. And he looked at it, and he said, oh, yeah, that's a satellite trail. I'm thinking, seriously? I mean, Hubble has a field of view that's literally this big, right? It's almost a pinhole, and the satellite went in front of it just when my data was being taken. I mean, what are the chances, seriously, right? It must be like 1 in a trillion. But in fact, it's not rare. So at the time, about 5% of Hubble images were affected by satellite trails. It didn't matter in my case. It was in a corner. It wasn't crossing the object I was interested in. So, I could happily ignore it. But there were other cases where actually these trails did damage the observation to such an extent to render them unusable. So that was my very first encounter. However, I think all of you might recently have seen more and more news reports that are related to satellites, and in particular, they related to debris from objects in outer space, in particular in near-Earth orbits. Why are there debris in outer space? Well, satellites collide with each other. The most famous, I think, satellite collision was between a defunct Russian Cosmos satellite and I think an Iridium satellite back in, I think it was 2009 or so. So 2 satellites colliding, they produced over 2,000 trackable large pieces of debris, and over 1,000 of those are still in orbit. And in fact, satellite collisions, explosions of satellites, because things do go wrong sometimes, weapon testing, these have produced tens of thousands of satellite debris that are actually actively being tracked by experts on Earth. So tens of thousands of debris. So these are things that are larger than, let's say, a tennis ball or so, but there's a million more that are not trackable just because they're too small and too faint, okay? And these debris can actually cause significant damage, not only to objects in orbit, but also to property and life on Earth. So some of you might have seen last November, I think, that there was a news report that was really widely reported by News Worldwide, where a Russian spacecraft attached to the International Space Station had to fire its thrusters to move the space station to a slightly higher altitude. And this was to avoid a possible collision with a very large piece of space debris that was from a satellite, I think a meteorological satellite, and no longer operational, that blew up in, I think, 2015. So that maneuver was successful. The collision was avoided, but you can imagine that had it not been successful, a collision of that type could have caused very serious consequences. It could have depressurized some modules on the ISS. It could have caused evacuation of the astronauts on board. So it could have caused not just significant property damage, but also loss of life. And again, just like I thought that the satellite trail on my HST image must have been rare, you might think, well, this must be a rare occurrence. It's not at all. So since the space station was first occupied in 2000, it had to enact maneuvers like the one that happened in November dozens of times to avoid possible collisions with space debris. And of course, space debris are not just a danger for the International Space Station, but they're a danger for every satellite that's out there, including the ones we rely on for our everyday activities, so GPS trackings and telecommunications, weather monitoring, and so forth. The other problem with space debris is on Earth. And again, this is a bit of Canadian news, which, however, was also very widely reported. So last April, several large pieces of space debris were recovered from a farm in Saskatchewan. And here's an interesting tidbit. This farm is owned, or is next to a farm that is owned, I'm not entirely sure, by an astronomer who used to work here at the National Research Council. She since moved to the University of Regina as a faculty member. So her name is Samantha Lawler, and since then, she studies objects in the solar system. Since then, Sam is a very strong advocate of the need to inform the public about the danger of satellite debris falling to Earth. Most of them will burn up in the atmosphere, but not the largest species. And you can find images on the web of these things. They were big. The largest one was 45 kilograms, so not the kind of thing you want to hit your head as you're plying your field, right, in Saskatchewan. So this was a piece from a SpaceX mission. SpaceX employees did come by, I would like to say under cover of darkness, but it was, in fact, in broad daylight. They came with a U-Haul truck, and I kid you not, and they just took away all these debris. And as far as I know, there was never really any communication from SpaceX to the public about this particular incident. So, do we need to worry about this? What is the situation? So in 96, when I was doing my PhD, there were about 600 satellites in orbit, okay? In 2019, so this is 23 years later, there were about 2,000. So in a time frame of 23 years, the number of satellites in orbit, active satellites, increased by just over a factor of 3, right, in 23 years. From 2019 to today, the number of active satellites is now 10,000. So that has increased by a factor of 5. So a factor of 3 in 23 years, and then since 2019, in 5 years, a factor of 5. So this is a huge increase in the number of satellites in low Earth orbit. So what happened in 2019 to cause this? Well, 2019 marks the beginning of the era of large satellite constellations. And these are large fleets of satellites that number in the tens of thousands of satellites, potentially, in low Earth orbits that are believed to be necessary to provide low latency, high speed internet connectivity across the entire Earth. And they do that very well. So 10,000 now. Of those 10,000, about 7,000 belong to SpaceX Starlink constellation. So there's 2 generations, first and second generation. The full fleet of Starlink satellites is actually 50,000 objects. So 7,000 have been launched, but the next ones are in the planning phase. About 600 satellites belong to the OneWeb constellation, which is a UK project. And that is one of the smallest, if not the smallest, satellite constellation that is either active or being planned. So if you think about that, the smallest satellite constellation is 600 satellites. That's how many satellites we had when I was doing my PhD in 1996. So just to put things into perspective. So Starlink is one project from one company, but if you look at the FCC and the ITU, which are the organizations that regulate telecommunications, there are filings with these 2 organizations for 21 satellite constellations from very many countries. The US is the major player, but the UK, France, China, of course, Korea, and many others. So 21 satellite constellations for a total of 560,000 satellites. So this is on the horizon, is potentially within the next decade. So 560,000 satellites. These are the satellites for commercial use. Behind the scene, there's a satellite for military applications, and of these we know nothing. But it's quite reasonable to assume that the military is also looking into fleets of tens of thousands, if not hundreds of thousands of satellites. Now, of course, not all of them will be built. Some of them will be built, but maybe on a smaller scale, so we're not necessarily looking at 1 million satellites within the next 10 years. But again, it's reasonable to assume that we might be looking at a situation where we have many tens of thousands, if not hundreds of thousands of satellites. And this is really a use of Earth orbital space in a way that has never been attempted before. And it's happening at such a pace and so quickly that we basically have had no times to set in place regulations or even to understand what the effects of these very large, with these huge deployments of satellites in low Earth orbit, what the effects actually are going to be. So, let me think what I was going to say next. So what are the impacts? I talked a little bit about the impact from space debris, and are we actually seeing the effects of this? And I would argue that we actually are. So for instance, between 2000 and 2020, there were 6 recorded cases of satellites that caused property damage on Earth. So there's many, many, many more satellite pieces that arrive down to Earth, but they don't cause any damage. And in fact, I think NASA had a study that showed that every day there is at least one piece of cataloged space debris that falls to Earth. But in the 20 years between 2000 and 2020, only 6 of these actually caused property damage, and in some cases, actually injury to people. So 6 cases. Every year since then, so from 2020 to today, every single year there have been between 3 and 4 recorded cases of space debris that have caused property damage. So every year since 2020, so since the launch of the very first satellite constellations, every year there have been as many cases of space debris causing property damage as there have been cumulative in the previous 20 years. And this is now being recorded for the last 4 years. So I don't think it's a statistical fluke. I really think this is a real trend. So we're already seeing the effects when it comes to space debris. And some of you, if you've read the news recently, in fact, the last one I saw was only a couple of days ago on CNN, I think, you might have heard about the Kessler syndrome. The Kessler syndrome is an hypothetical scenario whereby, which was proposed back in the 70s, I think 78, by a NASA scientist by the name of Donald Kessler. And what Kessler hypothesized was that if you crowd an orbit above a certain limit, then satellites will collide. So 2 satellites colliding will produce a large number of fragments. Remember the example I gave you earlier, over 2,000 fragments from that one single collision. These fragments will hit other satellites. That will cause more fragments, and this will basically trigger a chain reaction so that all these pieces of debris will end up destroying every satellite in that orbit. And that essentially will make that orbit completely unusable. So you can no longer launch anything in that orbit because whatever you put there is going to be destroyed immediately. You can't launch anything through that orbit. And Kessler hypothesized that if you take this to the extreme, this might actually mean the end of the space era, just because you cannot launch anything anymore. Now, this might sound like science fiction, it might sound really, however, there are experts, of which I am not one, but there are experts that actually think that if we're looking into hundreds of thousands of satellites in low Earth orbits, that might indeed trigger the Kessler syndrome. So it's something certainly to be concerned about. Okay, so I talked about mostly about satellite debris, but there's a lot of other potential impacts that these satellites might have. And the very first one is actually environmental impact. These satellites have to be launched. Now, Starlink, for instance, each spacecraft has a lifetime of about 5 years. With a fleet of 50,000, that means that just to replenish the ones that are no longer operational, you have to launch 10,000 satellites each year, and this is one satellite constellation. So basically, launches are going to become a daily event, and launches can be really detrimental and really cause extreme pollution in the upper atmosphere. There's a lot of gases that are being released as well as particles. On re-entry, the same thing might happen. So on re-entry, the satellites are designed to actually to disintegrate, essentially. But satellites have paints, they have resins, they have batteries, and these things don't just vanish, right? They are deposited in the upper atmosphere, and we're only now starting to study, again, not me, this is not my field, but people who know what they're doing, they're starting to try to understand what the environmental impact of this deposit of particles in the upper atmosphere is going to be, what the effect on the ozone layer, for instance, is going to be. And it could very well be, don't get me wrong, it could very well be that people are going to look into this and think, yeah, it's not a big deal, right? Compared to everything else we're doing to the upper atmosphere, this is not something we need to worry about. That's quite possible. The point is, we do not know yet. And if we wait to know that there might be a problem when we have launched all of these satellites, it might be too late. I actually heard an analogy some time ago, and I can't remember where, so I'll try to find the source. But basically, this person said, we're basically behaving towards outer space the way we used to behave with the oceans. So we used to throw all kind of trash and plastic in the ocean because there's so much water out there and it's an infinite resource. But it's not. It's not an infinite resource. It's a very finite resource, and we can cause serious and irreparable damage unless we're careful about what we do. And we're now behaving with outer space the same way that we used to behave and still do to some extent with the ocean. There's, of course, impact to professional astronomy and to astronomical research, and that's my first encounter with a satellite. Satellites are bright. They reflect sunlight in every direction, including down to Earth. The very first generation of Starlink satellites was very bright. Their magnitudes, if any of you is an amateur astronomer or a professional astronomer, they were about 2 to 3. So there's, I'm going to say, less than 100 stars in the sky that are brighter than that. So they were visible, very visible by the naked eye. They're now a lot fainter. They leave trails in your images because they move across the sky with a speed that depends on their orbit and their altitude and so on and so forth. Now, how serious is this? It's probably not as serious as you might think, because of course of all the satellites that are out there, only a fraction are going to be above the horizon at any given time. You're not going to see all of them all the time. And also because they are in a low Earth orbit, they're mostly visible at the very beginning and the very end of the night. So they're not visible in general in the middle of the night. How much damaging this is to astronomical research very much depends on the observatory you're using. It depends on the instrument, how sensitive the instrument that you're using is. It depends also on the science that you're trying to carry out. So, for instance, smaller telescopes with instruments that are not very sensitive, they're probably not going to be affected all that much, even with fleets of a few tenths of thousands of satellites. When we are in the hundreds of thousands, it's a whole different ballgame. But you can always, if you know where the satellites are going to be, which right now we do not, but if you do know, then you can avoid them. You can just schedule your observation to avoid the parts of the sky where the satellites are, and you do something else in that time and then come back to it. However, this is not always true. So there are observatories that are going to be significantly affected. So some of you might know about the Vera Rubin Observatory, which is built in Chile. It's going to see first light in June of this year, and many of us are really waiting quite eagerly for the data from Rubin. It's really going to be revolutionary in many ways. Rubin has an extremely sensitive camera, and it has a huge field of view. So the field of view of the camera on Rubin is 3.5 degrees. So for scale, the full moon, the diameter of the full moon is 0.5 degree. So this is really a big chunk of the sky. And it's going to observe the entire sky visible from its location every 3 days. So it really is going to be like nothing we've ever seen before, right? So for Rubin, it's very difficult to avoid satellite trails. And current simulations that use the full fleet of Starlink satellites, so about 50,000 satellites, show that between 30 and 50% of data taken with the Rubin Observatory at the beginning and the end of the night is not going to be usable. And that's a huge loss of observing time and ultimately of money, because these observatories are actually costly to operate. If we have a fleet of 500,000 satellites, we might as well close down the observatory, essentially. There's just not going to be enough usable data taken by Rubin to make it worth it, essentially. So it could be very dramatic in that case. It also depends on the science that you're doing. For instance, if you are searching for asteroids that might impact Earth, those are visible at the beginning, at the end of the night, which is exactly when confusion from satellites is at its worst. So studies of the solar system, in particular faint objects, for instance, beyond the orbit of Neptune, are going to become much more difficult if you have very large fleets of satellites in space. So all of this is really, concerns optical astronomy and imaging, but infrared astronomy is compromised as well because the satellites are bright and they emit, warm and they emit in the infrared. Radio astronomy is severely compromised, and this is because these satellites communicate with the ground through radio waves. And astronomy has some radio frequencies that are protected. They're for the exclusive use of astronomy. However, there's leakage from this radio transmission into these bands, and it's very, very hard to correct for these. So, in fact, the damage to radio astronomy, the impact, I should say, to radio astronomy is potentially more severe than the impact to optical astronomy. There's another effect that I think is more subtle, but also important for reasons that I'll come to in a second. And that is that you might think, well, why don't we just make the satellites really faint with coatings, for instance, or whatever? And indeed, this is being done. But in fact, even faint satellites, you might no longer be able to see them as point of lights that move across the sky, but they still raise the overall brightness of the night sky. So you can think of this, if you are in a street and there's light bulbs, you see the light bulbs as individual sources of light. But if you move away, they become fainter. At some point, you no longer see them as sources of light, but you still see the overall glow of all the light bulbs in a city. And indeed, as you know, if you're just outside the city center, for instance, very often you're not able to see stars. You certainly are not able to see the Milky Way or anything like that. So increasing the brightness of the night sky actually limits your ability to enjoy a pristine view of the sky itself. How serious is this problem? Right now, it is not. So with 10,000 satellites, the brightness of the night sky increases by maybe 1%, and that's really in the worst case scenario, at the particular time of night in particular locations. However, if we're now talking of several tens of thousands, maybe 100,000 satellites, and then when you add the contributions of all the space debris, which, they're no longer active, but they still reflect the sunlight, then you might be looking at an increase in the brightness of the sky of 10%. And this is actually significant. This is noticeable. And this brings me to my next point, that professional astronomers, there's not a whole lot of us, so who cares? But professional astronomers are not the only people that look at the night sky. There's, of course, amateur astronomers as well, but astronomy has very deep cultural ties as well. The International Astronomical Union, which is the worldwide organization of professional astronomers, celebrated its 100 years in 2019, and the slogan for the event was "Under One Sky." And this is not just a catchphrase, it's not just a slogan. It really meant to signify that the sky unites us as human beings. It's something that is a resource that we all share and we are all entitled to. And the IAU, so the International Astronomical Union, has sponsored thousands of events that have reached millions of people, in particular school children. And these events that are all based on the observations of the night sky have really changed the attitude of students towards STEM subjects, for instance. They have provided economic benefits to remote locations through astrotourism. And they have brought together people from different cultural backgrounds, from different religions, different parts of the globe, all united into observation of the sky. There's something almost primeval when you really look at the night sky. It's something that really touches you in ways that other, for better or worse, other science can't really do. So we are at risk at losing this. Okay. Indigenous cultures, for instance, many of the teaching of indigenous cultures are based on observations of the constellations and of the night sky. So this is something that needs to be considered. There's also an impact on biology and on species on Earth. So there's a lot of studies, again, not my field, but there's a lot of studies on ecological light pollutions. So it's well documented that there's massive death of birds, for instance, because of lighted structures on Earth. Or hatchling sea turtles will die because they get confused by bright lights on their native beaches. There's, if you can believe this, there's beetles, so there are insects that orient themselves based on the light from the Milky Way. So if we do remove access, pristine access to the night sky, then we are potentially causing problems for not just for humans on Earth, but for every living being on Earth. Again, is this a problem? We don't know, and that's the whole point, that we have not had the time yet to assess what the impact of these huge satellite constellations is going to be. We're just starting to do it, and we can't quite keep up with the pace at which these things are being launched. How long have I been talking? Okay. 34 minutes. So do I have another 5 minutes? Okay. Because I wanted to also talk a little bit about the legal framework. So what is being done about this? So outer space is known as a commons, and a commons is a common resource that is not owned by anyone in particular, but belongs to all of humanity. And commons are subject to an economic and environmental theory, which is known as the tragedy of the commons, which basically states that it is possible for an individual or individuals to overuse a common resources to the point of depleting it or destroying it. And to avoid the tragedy of the commons from happening, there are treaties that regulate the use of commons. So, for instance, the continent of Antarctica and the high seas are commons. They don't actually belong to a specific nations. And there are UN treaties that regulate the use of both, the Antarctic Treaty and the Treaty on High Seas. Outer space is also a commons. It does not belong to any single country. It's really a gift to all of humanity. And so, just for other commons, there is a UN treaty that regulates the use of outer space, and this is called the UN Treaty on Outer Space. And it's a very general set of rules. So for instance, it does state that outer space is not the province of any single country or nation, but it's free for exploration by all. It does prohibit the use of nuclear weapons in outer space. It does set some financial responsibilities for damage that is caused on Earth by objects in outer space and things of this nature. So the Treaty on Outer Space was signed in 67, I believe, 66 or 67, so about 10 years after the beginning of the space age, which was in 57 with the launch of the Sputnik 1 satellite. Since then, there have been a number of UN declarations on the use of outer space. So I'm going to read you a couple of them, if I can find them. So in 94, UNESCO had a meeting in the Canary Islands and adopted the so-called La Laguna Declaration, which includes this statement, and I'm quoting, persons belonging to future generations have the right to an uncontaminated and undamaged Earth, including pure skies. They are entitled to its enjoyment as the grounds of human history, of culture, and of social bonds that make each generation and individual a member of one human family. Following this, there was a UNESCO declaration as to the responsibility of current generations towards future generations, basically stating that current generations should not engage in activities that can limit the ability of future generations to enjoy these common resources. In 2007, after another summit in the Canary Islands, there was another declaration called the La Palma Declaration, which has the following statement, and again I'm quoting, an unpolluted night sky that allows the enjoyment and contemplation of the firmament should be considered an inalienable right, equivalent to all other social, cultural, and environmental gifts. And it also urges nations to adopt the pertinent standards for preserving the quality of the night sky. So the right words are there, right, black and white, but really at the time, no one really envisioned a use of outer space at the scale that we're now, that we're basically seeing today. So there really is no legal framework to protect the night sky from satellite constellations. And there are, liability treaties. So for instance, there is a treaty that says that any material damage to Earth is the financial responsibility of the country that has launched the satellite that has caused the damage. But these treaties really don't extend to non-material damages, like the loss of the ability to look at an uncontaminated night sky. And, you might think, good grief, what's the big deal, right? When the light bulb was invented, I'm sure lots of people were saying, oh, we're no longer going to be able to see the stars, and it's going to be a tragedy and whatever. And here we are. And we've all survived and we've all carried on. So what's the big deal? Isn't that the same thing? It is actually quite significantly, fundamentally different, because when cities started to be lit up, astronomy moved to rural areas. So there's still a lot of places, although fewer and fewer, to be honest, but a lot of places on Earth where you do have an uncontaminated view of the night sky. But satellites are visible everywhere, so we have these private commercial interests that are basically depriving everybody of the ability to actually look at an uncontaminated sky. So what are we doing about this? There's many different efforts that are ongoing. The ones I am most familiar with are the ones that are sponsored by the International Astronomical Union. A few years ago, the International Astronomical Union has started a center which is called the Center for the Protection of the Dark and Quiet Skies from Satellite Constellation Interference, or CPS for short. And the CPS is based in Arizona. It's a collaboration between the IAU and NUAR Lab and the SKAO, which represent the interest of the optical and radio astronomical community. And CPS is not just a collection of astronomers, because that would be pointless. It really brings together professional astronomers, but also satellite operators, policymakers, and the wider community, and really acts as a bridge among all of these actors to try to understand what the consequences are for each and trying to find solutions and mitigations to potential problems. And there have been results. So for instance, I mentioned earlier, the very first generation of Starlink satellites was very bright. They're no longer that bright now. So the second generation of Starlink satellites is over about 100 times fainter than the first generation, even if the satellites themselves are larger. And this is because of coatings on the satellites themselves. And this resulted from discussions between CPS and other people and the StarX people, which to their credit, because they didn't have to do this, but to their credit, they did adopt these mitigation strategies. And as a consequence of that, we now have not as serious a situation that we would have had otherwise. CPS is also an advocacy body, so the CPS director, Piero Benvenuti, is often talking at meetings of COPUS, which is the UN Committee on the Peaceful Use of Outer Space. And as a consequence of the efforts of the CPS, the impact of satellite constellation on astronomy is now a standard item at every meeting of COPUS, when in fact astronomy was never on the horizons before. So we are making progress. There's a number of okay, I won't go because the microphone won't. But CPS has also produced a number of publications that are aimed to the general public, but also to politicians and to policymakers. I have some here if you want to live through them. And so we definitely have we've had, I think, a positive impact. And there's a number of mitigation strategies that have been proposed. Some of them have been adopted. Some of them have not been adopted yet. So I'll stop here, but I will just leave you with one final thought. And that is, have we not learned something from previous history? I mean, you think of aerosol, fossil fuels, plastics, pesticides. These are all things that really improve the quality of life on Earth, right? There are things that have been tremendously useful. Now, many years after we started using all of these things, we realized, this comes at a cost, right? Sometimes a very high cost. So now we know this, and we're trying to remediate the situation. Had we thought about this at the very beginning when we started using pesticides, for instance, perhaps we would have had regulations in place that would have curtailed the side effects, and we would not have to scramble many years down the line to try to remediate the situation. So we are about the same, in the same position now with the use of outer space. What's the rush, in some sense, right? These satellites constellation provide a terrific service because they do bring very fast internet access to very remote locations for the very first time. So there's clearly is a very great use of them. But why not slow down until we really understand what the side effects are? And if they turn out that we're worrying about nothing, great, then we can go ahead. But if there are serious consequences from the launch of these satellites, then we can proceed in ways that mitigate those effects. So I'll leave you with that, but I have actually, I have a Google Doc where I've compiled a number of links. It's not a very long list, it's about a dozen or something. It's not a complete list by any stretch, but it's a starting point. So for those of you who want to learn more about this, you're welcome to go to that Google Doc. And hold on. I have here a QR code, and I didn't make many copies of this, but you can take a copy. If it's the last one, just take a picture of it. So if you scan that QR code, that will take you to that Google Doc with all the links. So I thank you very much. I hope I didn't bore you too much. And again, if you have any questions about anything I talked about, I'm very happy to try to answer them. Thank you.
Thank you for a fascinating talk. I'm sure there's going to be a lot of questions, so please put up your hand if, and you just go ahead and, yeah.
One thing you didn't mention, I know there are a number of places around the globe where they have dark sky parks, and there's been, recent news about encroachment on those parks. Did you have any other information about those or thoughts about?
Encroachment from satellite interference? Or?
Well, from infrastructure, from
Oh.
people wanting to use,
Well, so we a little bit at a time we are losing the night sky. For very many years, for instance, there were really no regulations on the use of street lights, right? So very large areas around cities are really not usable for astronomical research. There are parts of Earth that are very dark. Right? I mean, if you think, like I work for the National Research Council, we have a telescope on site, which, I mean, Victoria is obviously quite bright, so it's really, it is used actually every night, but not really for breaking research anymore. So there are areas that are very dark. Of course, for astronomy, you don't just need a dark site. You also need high elevation. You need to have certain weather conditions. So there have to be a number of things that come together. But there are dark sites. There are also radio quiet sites that are preserved. It's fewer and fewer, but at the same time, because we are becoming more and more aware of this light pollution, then there's now regulations that are put in place to try to limit. So, for instance, orienting light bulbs in lampposts downwards, right? Or using certain types of lights and so on and so forth. So I think that's a struggle, but it's a battle that is being fought. But when it comes to satellite, then there is no safe space, right? So that's quite different. Yes.
You talked about the Tesla syndrome, and
Yeah.
we've seen it from movies and so on, but in the case of satellites, to a small degree, would there be impact for us here? Would we see something? Would it potentially change climate? Would there be anything that would stem from that?
So I don't know if everybody heard the question. Okay, so the question was about the Kessler syndrome and whether this is going to, if there's going to be any impact, like on the climate or on us on Earth and whatever. I don't actually know the answer to that. There's certainly, I can imagine, there's certainly going to be an impact on Earth because these pieces of satellites are not going to stay in orbit forever. The amount of time they stay on orbit depends on how high they are. So very high orbits. Sometimes people dispose of satellites by moving them to what are called graveyard orbits that are very, very high, and satellites can stay there for tens of thousands of years, so it's going to be someone else's problem. But in low Earth orbits, they actually decay rather quickly. So I can imagine that if you do have a very large number of debris, you are also going to have a significant impact on property on Earth. But in terms of damage to, or effects on climate or anything like that, I actually don't know. Yes.
Hi, let's meet it, Dr. Rodgers. It's beautiful to have you. Let's meet it. I have two questions. One has to do with cybersecurity and how, if in fact the satellites fail and the collisions are caused by man-made cyber attacks, is that like a clear present danger? Is that a problem with the engineering protocols? Years ago, I met a gentleman that worked with Elon on the Summit Space. He was a NASA scientist that explained how the suborbitals are launched. But in fact,
Okay, so the first question was whether we should worry about cyber attacks and someone taking control of these satellites in space and potentially causing them to collide with each other. I would think that that is a concern. I don't actually know, but it's certainly not an impossibility, it seems. I will also say that you don't even need, evil actors to cause a lot of problems because so satellites that are no longer operational, even if they don't work, you can still have control of them up to a point. At some point, you actually lose control entirely, and then it's basically random, right? Yeah. So basically, there are now regulations that are being put in place so that you have to decommission decommission. So either re-enter or boost them to a higher orbit. You have to do that within 5 years of end of mission, which was not the case before. So you could just leave them there, right? Now this is a step forward, but as I mentioned earlier, it's not great because on re-entry, these satellites do vaporize or anyway. So they do deposit a lot of material in the upper atmosphere. So in terms of cybersecurity, I can certainly imagine, again, not my field, but that it will be possible for someone to actually, with bad intention, to actually do that. For the black hole question, so I'm not sure I understood it.
And is the effect of the center of the galaxies created by the super black holes, or is there a volcanization effect happening where everything's attracted by what I know about astrophysics, a swirling eddy that allows for those heavy, like metallic moltenized gases and moltenized materials to come to the middle and form the centers of our planets and our universes, and allow for those layers to happen in these forms vulcanized, like a covalent system of nuclear reaction after nuclear reaction that allows for all these things to be coalesced.
Yeah, so I think the question is basically how do the supermassive black holes, how do they behave, right? What are the processes that we study around supermassive black holes? And does this have anything to do with how the universe formed, basically, right? Sorry, maybe that's...
Is it superinduction, volcanization? Like, is there some type of thesis that you could discuss now instead of us waiting?
Right. So black holes, they really don't behave any differently from anything else in some sense. So what they have is a mass and no size. And so the only difference between, let's say, a black hole of, let's say, 10 solar masses and a star of 10 solar masses is that in a star of 10 solar masses, you can only get so close because you get to the outer boundaries, let's say, of the stars, and then that's it. The closer you get, the less mass you have in between you and the center. For a black hole, you can get right against it, right? So you can move material much faster around a black hole of any given mass than you can around a star of the same mass, for instance. But that's the same thing. It's not as if a black hole is just going around sucking things from everywhere, right? The gravity is the same. You can just get closer. And that's the reason why you can produce this very large amount of energy from material that spirals towards the center of a black hole. Black holes do merge, although I don't actually think we have concrete evidence of that, but when galaxies merge, people believe that black holes will come together and they will eventually merge, right? How black holes relate to the universe itself, we don't actually know, or at least I don't. What we also don't know is how black holes form. We know how stellar mass black holes form, so those just form from the evolution of massive stars. But these very massive black holes, we don't actually know how they form. And it's actually a really interesting question because we see some of these very, very massive black holes when the universe was very, very, very young. So we really do not have a lot of time of forming all these, putting all of this mass together. So how they form is actually pretty much unknown. There's a few theories, but I don't think we yet know the answer. So I hope that.
Back to me, that's beautiful. The infrared imaging that's coming in, it's amazing. Because when I went to the center here, I'm from Ontario, it's the understanding of like these beautiful minds like you to share with us. Thank you.
Yeah, thank you. Okay, are there any other questions?
I have a quick question.
Yes?
I'm just curious, do people insure satellites? Is there an insurance industry in space?
I think you've just identified a business opportunity there.
It just seems like the insurance industry is what's driving a lot of change and financially creating disincentives to do crazy stuff.
It's possible. I don't actually know.
Don't insure satellites as far as you know.
I don't know. It's.
Yeah,
Okay.
there's a-
Oh, sorry.
So this may seem like a naive question, but so is there a relationship between, like when I look at the galaxy picture, I see a vortex. So is there a relationship between the strength of the supermassive black hole at the center of the galaxy to the circulation?
Oh, that's an excellent question. Very good. So the question is, so you look at the galaxy and you see spiral arms and whatever. Is there a relationship between the black hole at the center and the rotation of basically the stars within the galaxy? Yes. And that is indeed why we know, or we inferred that the evolution of supermassive black holes and the galaxy in which they reside are strongly coupled with each other. So I don't have a graph, but so one of the papers that we published shows that the mass of the black holes at the center of galaxies correlates very strongly with the rotational velocity of the overall galaxy. Well, that was not exactly correct, but it's close enough. And this is a surprise, right? Because, as I said, the black hole is at the very center, and you're looking at the velocity of stars way out in the galaxy. It would be like saying that, the traffic in Toronto depends on the traffic in the parking lot out here, or the number of people that are out here. It just doesn't. It's not obviously. The two are not obviously correlated, right? What that means is that the mass of the black hole is related to the mass of the galaxy, because the mass of the galaxy is so how fast material is rotating within a galaxy depends on the overall mass of the galaxy. If the galaxy is more massive, things rotate faster, right? So it's that correlation, the fact that the mass of the black hole correlates with the mass of the galaxy, that tells us that there is a coupling between the two. So that's you spot the thing exactly.
Can I please add to that?
Yes.
Can I please add to that and just saying, is that a gyroscopic, like the gyroscopic XYZ plane, and is it expanding inwards and outwards like this ever-expanding blob, right, in all directions?
No, it's it really, there is nothing as exotic as that. So it really is just that the mass of the black hole. Well, I was going to say larger, but what I really mean is more massive galaxies have more massive black holes at the center, and this is not necessarily an obvious fact.
So I'm sure there's many more questions, but let's thank Dr. Laura Ferrarese at this time. And I think she'll be here for a while if you want to come up to her and ask her, and get the QR code as well.
Yeah.
Okay.
Well, I left them here.
There, yeah,
Sorry.
okay, they're right down
I
here.
left them
Yeah.
here, but and you're welcome to. If there's only one left, please leave it there so other people can actually take a picture. But
Thank you.